little bit maximize.
Very good. Okay. So is
Yeah,
it?
it's okay. It's fine, sir.
Very good. So we talked about this breakdown of Cauchy linear. This is ut plus c of u, ux equal to 0. This is quasi-linear partial differential equation, the simplest one can think of. This is the simplest equation one can think of, which is linear in the highest order derivatives, but non-linear in u, satisfying this condition that ux0 is u0 of x. T is greater than 0 and x is in R. This is the problem, okay? And we noticed that the solution breaks down after a finite time, and we could find this time. This is time of breaking, that is minus 1 upon f dash xi. And what is f? F of xi, it was defined like this, c of u0 of xi. And what is the solution of this analytical form of the solution? The analytical form of the solution was this: t is equal to x is equal to xi plus t f of xi, and u is equal to u0 xi. This is the analytical form of the solution of initial value problem 1. Is that right? The solution breaks down after a finite time, where f is this expression. So f dash would be your c dash into u0 dash xi. This is the expression for f dash, right? This is your f dash. No matter how smooth is the initial solution, yesterday we considered an example. It was 1 upon 1 plus x square, which is infinitely differentiable function, but the solution breaks down after a finite time, and we could find that after t is equal to, I don't remember some value, it was 8 by under root 27. Was that right?
Yes, sir.
The solution breaks down. Yeah, very right. So the thing is this: how we can extend the continuity of the solution? So the problem is how to extend the continuity of the solution, or how to extend the solution. How to extend the solution of 1 beyond breaking time. This is a real problem. Solution breaks down, but how to extend the validity of this solution? How to extend the, I will write validity. The validity of this solution beyond this breaking time. So for that, so it's very clear, you see, I told you in the beginning that there are examples of evolutionary equations, the solutions of which satisfying an initial data, no matter how smooth, always exhibit a discontinuity, right? Although, I mean, when you construct a model, right, a mathematical model, it is assumed that the variables which describe the state of a system are sufficiently smooth. But there are examples where it is not so, and this is an example you can see here. So what happens, in fact, some assumption which was used in the beginning is no longer true. You see here in framing or in developing this mathematical model, we assumed here u is the variable which describes the state of a physical system, right? And we assumed that u and its partial derivatives are sufficiently smooth, whereas it is not so. You see the differentiability, that ut and ux, they become unbounded after a finite time. So in fact, this model itself breaks down as a matter of fact after a finite time. So what is the solution to this problem? The solution of this problem is to look that reformulate this model as a matter of fact. We have to reformulate. That is, what went wrong in this formulation that we have to see? Because initially we assumed that u and its partial derivatives are continuous, but this is no longer true after this t is equal to tb. So we have to reformulate, look at the model again and see what went wrong in this formulation, reformulate it, and then proceed further in order to extend the validity of the solution beyond this breaking time. So we are doing this exercise. So it's very clear that first of all, it's very clear, since the gradients become infinite at t is equal to tb, the solution beyond this breaking time cannot be of class C1. It's very clear. It cannot be of class C1. No. So we have to extend the notion of solution itself, right? Here the notion of solution is this, a function u, which is such that it satisfies it identically, means u has a continuous partial derivatives. Ut and ux, they exist, not only exist, but they are continuous also, right? Isn't it? By solution, we mean this. We say C1 solution. This is the definition. So we have to forego, you see, this notion of solution, and we have to generalize the notion of solution. Now we shall be looking for those solutions which include discontinuities as well, right? What to say of smoothness? Even the function, I mean, the variable may be discontinuous. So such solutions, they are referred to as weak solutions, right? We want to extend the validity of the solution beyond this breaking time. So for that, the first thing that we would like to do is to extend the notion of solutions. We are interested in those solutions which include discontinuities as well, and such solutions are referred to as weak solutions. Now, all right, so we extend this definition of smooth solutions. Now we are not looking for smooth solutions, we are looking for weak solutions. So for what is the next thing? The next thing is this, that we should write this equation in the conservation form. In the conservation form. Conservation form of one. One, when I say one, means this partial differential equation, not the initial condition. Is that right? I would like to have a conservation form of one. So what is conservation form? Conservation form, you may recall, this is the conservation form. Dy of f of u is equal to 0. This is, we say that this is the conservation form. U is called the density function. U is called the density function, and f of u is called the flux function. So you see, this represents a very general conservation law. U may be a density, mass density, right? It may be momentum, it may be energy. So this may correspond to conservation of mass, conservation of momentum, conservation of energy. Is that right? What it says, that rate of change of total mass of this density function is balanced by the net flux across the boundary, right? Across some boundary, I mean, it is balanced by the net flux. So here it is a one-dimensional flow, means the situation is somewhat like this, that yes, at these two stations, say x1 and x2, it is a one-dimensional flow. So x1, these are the two stations, right? Suppose these endpoints, we are interested in finding out the solution between x1 and x2. So the rate of change of this entity, what is the conservation form? That is the rate of change of this entity, ddt of x1 to x2 u of xt dx. What is u? U is the density function. Now it is the mass per unit length, right? Length is from x1 to x2. So this is the total mass. Rate of change of this total entity is balanced by the net flux. What is flux here? F is the flux function. So f of u of minus f of u of x2 comma t, right? x2 comma t means the flux entering this station x1 and the flux leaving this station x2. Rate of change of this total entity, this is total mass, is balanced by the mass flux. It could be the momentum flux, it could be the energy flux. So you see, this is the integral representation of the conservation law. This is the integral representation of the conservation law. This is in the differential form. This is the conservation law in differential form. This is the corresponding integral representation. Is that all right? Look here, star and double star. This is the differential form of the conservation law, and this is the corresponding integral representation. You pick up any book on physics and you will find that these laws, right, the rate, I mean, whether conservation of mass or conservation of momentum or conservation of energy, they are derived in integral form, not in the differential form. They are first defined, right, in integral form. Why? Yes, there is a reason. There is a reason. What is the reason? Somebody can tell me. Hello? Hello?
Yes, sir.
Somebody can tell me. You see, if you pick up a book on physics, you will find that these conservation laws, they are derived in integral form, right? Not in differential form. Differential form follows. If I assume that u and its partial derivatives are continuous, then this star follows. This form follows from here. This form follows from here because if I allow this, if you replace x2 by, hello, x2 by x, replace x2 by x. I assume that u and its partial derivatives are continuous.
Yes, yes.
And ddt of this left-hand side, look at the left-hand side. The left-hand side would be your, yes, by Lebanese rule, hello? By,
Yes, sir.
this will be your d by u
Day
by
one.
d by t.
Yes.
Is that right?
Into dt. Yes.
Yes. So this is, I mean, this partial derivative, this is taken inside, okay? This is taken inside this, and it's, hello? This is the first term, plus you get something. Is that right? Hello? Hello?
Yes, sir. Yes, sir.
Okay. So now if I differentiate the right-hand side, of course, it is saying u at x1 comma t minus f of u x2 comma t. And if I differentiated this now with respect to x, so what it would be, from here you will get f is a function of u and x, x1, x2. x2 is replaced by x. This is x. Here it is x1. So when I differentiate this with respect to x, yes, because x1 is a fixed constant. So this is the first term, that is minus d by u. Am I right? D by f, d by u into d by u, d by x, the second term. And what happens to this? The fundamental theorem of calculus tells us integration and differentiation, these inverse processes. So it gives us d by u, d by t
Equals
minus, and it is nothing but c dash, right? It is nothing but f of u into, yes, is it all right? Hello? By j down f dash. So in fact, the partial derivatives are same in this case. Minus df du into ux. So is it all right? Hello? So we recovered this case. That is, this is the differential form of the conservation law, and this is the corresponding integral representation.
Yes.
Now, if I assume that u is of u and its partial derivatives are continuous, then the original differential form follows from here. But this is more general. Look here, the differential form is meaningless for functions which are not differentiable. If suppose u is not differentiable, this is meaningless, and much more if they are discontinuous. Is that right? This differential form is meaningless for discontinuous functions, but this integral representation makes sense even for discontinuous functions. Here you see, it asks only for integration, that integrals should exist, and we know that discontinuous functions, they are integrable. Hello?
Yes, sir.
So this is more general. So now, instead of taking this differential form, we will focus on the corresponding integral representation. So what did I say? That this one breaks down after a finite time t. So it is very clear that some physical assumption, some physical hypothesis which we imposed in the beginning, that the partial derivatives, their etc., 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 they are no longer valid. So we have to reformulate this model. And in fact, this is the reformulation. We look for the corresponding conservation law, not on differential form, but in the integral representation form. Is it all right? Hello? Why? Because it includes discontinuities as well. And it is very clear from our analysis that the solution cannot be of class C1 beyond this time t is equal to tb. It might include a discontinuity as well. And therefore, it would be appropriate to use an integral representation of the conservation law. This is the reason. Is it all right? Hello? Okay.
Yes, sir.
So now now I will show that in this representation, it is possible that there might be a discontinuity between x1 and x2, across which u and its partial derivatives may be discontinuous. U and its partial derivatives may be discontinuous. All right. So let us consider this situation. This is your x1, this is your x2, and then there is a curve between x1 and x2. Let me call this as x is equal to x of t. This is a smooth curve across which u and its partial derivatives, they are discontinuous. If this happens, then what kind of restriction is imposed by this conservation law? That we have to see. This discontinuity cannot be arbitrary, right? This has to be fixed. I mean, it should depend on something. Let us see that what are the restrictions imposed by this fact that the partial derivative, u and its partial derivatives may be discontinuous across this curve. All right. What do we notice? We can write this. Yes, first of all, this is the first step. That is d dt of, look here, x1 to x2. So a discontinuity is fitted between x1 and x2. X varies from, if I start integrating from x1 to x2, x1 varies from x1 to x of t, and it is u of x comma t dx, right? Plus the second term, that is d dt of, this is capital of xt and x2. This is u of xt dx, and right hand side remains the same.
Sir, move the paper upside.
Oh, sure. Is it visible now clearly?
Yes, sir.
All right. So f of u of x1 comma t minus f of u of x2 comma t dt d. All right. Okay. Is it all right? Now, you see, now you have, I think, understood the sequence. The differential equation, right, that we considered initially, this solution becomes discontinuous after a finite time. To extend the validity of the solution beyond this breaking time, we have considered the integral representation of the conservation law, which is such that when u and its derivatives are continuous, we recover this form, right? And this is general in the sense that its solution, it involves derivatives, right? This allows the discontinuity in u as well as its derivative. If it allows the discontinuity in u and its derivative, right? Suppose x is equal to xt is a curve across which u and its partial derivatives are discontinuous. Then this conservation law can be written like this. Is it all right? Hello?
Yes, sir.
Okay, very nice. So this allows us to, now here you see again, make use of Lebanese, yes, make use of Lebanese rule. So the first term, now look here, this is to be noticed that in this region, which is on the left, and this is on the right of this discontinuity. On the left, the differential form is applicable. Hello? Here you see, because u and its partial derivatives, they are of class C1 on the left. And if it is so, then both are equivalent. This leads to this. Is it all right? So this differential form is valid here. The differential form of the differential form of this conservation law, it is valid here. Only there is a problem at the discontinuity, because this differential form is no longer valid on the discontinuity x is equal to xt. Is it all right? Hello?
Yes, sir.
Okay, very nice. So let me write by making use of Lebanese rule. What do we get? Day5 day5t, right? Day5 day5t. This is xt dx, and this is your x1 to capital X of t minus, okay, or this is all right. The next term in the Lebanese, okay, formula, what it would be? The function evaluated at the upper limit. So I will write this as u xt. Now you see x1, x2, right? x1 approaches, so x1 approaches the discontinuity from left. So this is the, okay, is it all right? Hello?
Yes, sir.
Yes, sir.
So this is the evaluation of u on the rear of x is equal to x of t. That is the limiting value of this as x approaches capital X from the left into dx dt. Is it all right? Hello?
Yes, sir.
This is the next term. The third term would be 0 because x1 is fixed. X1 is fixed. Is it all right? Hello?
Yes, sir.
Okay, very nice. So then similarly we can expand this, apply Lebanese rule. So what do we get? The first term would be 0
Yes.
because x2 is fixed.
Yes, sir.
All right, let me write the integral term first. Day5 day5t at xt, this is dx, and this is your xt to x2, this is the first term. The second term would be with minus sign, because now here this will be 0 and this is with minus sign. So minus, what do you get? Minus, hello, u evaluated at the lower limit. U evaluated at the lower limit, I will write like this, u xt with plus sign. Is it all right? U evaluated at x2, that is x approaches capital X from right, as x approaches capital X from right. Is that right? So I will write plus sign. That is the evaluation of u at the discontinuity as x approaches the discontinuity from right. Is it okay? Hello?
Yes, sir.
So this is the term multiplied by dx dt. Dx dt. Is that right? Right hand side, of course, it is f of u of x1 comma t minus f of u of x2 comma t. Is it all right? Hello?
Yes, sir.
On this.
Okay. Now, keeping in mind that in this region, in this open region, x1 to capital X, in this region, right, this day5 day5t is given by the differential form. This is nothing but minus day5 x of f of u. Is it all right? Hello?
Yes, sir.
So this is your x1 to capital X, and this is your u. Now you see, what is this? If you look at it, it is nothing but the limiting value of u as x approaches the discontinuous curve from left. I will call it ul. Is it all right? What is ul? U sub l, the limiting value of u as x approaches the discontinuity from left. I will use it ul just for the sake of convenience. Is it all right?
Yes, sir.
This is dx dt plus, now similarly here I will write capital X to x2, and day5 day5t is minus day5 x of f of u, right? Its derivative with respect to x dx. And so this term is taken care of, this term, there is one more term, right? Minus, now look here, this is the limiting value of u as x approaches capital X from right. I will write as u sub r. U sub r. Is it all right? So the meaning is very clear. ul and ur, these are the limiting values of u as the discontinuity is approached either from left or from right. Is it okay? Hello?
Yes, sir.
All right. So dx dt, this is your f of u of x1 comma t minus f of u of x2 comma t. Is it all right? This step is clear? Hello, is it clear to all of
Yes,
you?
sir.
Yes, sir.
Now make use of fundamental theorem of calculus. Integration and differentiation, these two are inverse processes, right? So what do we get? The value of f evaluated at the upper limit. So f evaluated at the upper limit.
fx.
So I will write, you see, what happens? X approaches the discontinuity from left. Is it all right? Hello?
Yes, sir. Yes, sir.
So f of ul as a matter of fact. So in fact, I will write that's f of ul. F of ul. Is it all right? Hello?
Okay, sir.
This I will write this. Okay, this is with minus sign. This evaluated at the upper limit. Minus sign is there. Minus its value at the lower limit. So it becomes plus. It is f of u of x1 comma t. Is it all right? Hello?
Yes, sir.
Yes, sir.
Similarly, the second term, of course, I can combine these two. Second and fourth terms can be combined. So this is your ul minus ur. This is your dx dt. And the last term, you see, the third term, again, what it gives me, let me write, minus this evaluated at the upper limit. That is minus f of, what do you get?
x2t.
U of x2 comma t. Am I right?
Yes.
Yes, sir.
Okay. And then its value at the lower limit with minus sign, so plus
Plus.
f of ur. Am I right? Hello?
Yes, sir.
Okay. What is the right hand side? The right hand side is f of u of x1 comma t minus f of u of x2 comma t. What happens? Is it all right? Hello?
Yes,
Any
sir. Yes, sir.
So you can see here
Cancel
that
out.
this term cancels with this. This term cancels with this. What remains here? I get a very nice formula, that is ul minus ur dx dt. This is equal to f of
ul minus f of ur.
Very right. Wonderful. So I can see this is called, in the literature, I will write this as f of u. The square brackets enclosing an entity means its evaluation on the left minus its evaluation on the right. This is the meaning. Okay, this is a matter of notation. Any entity means this entity evaluated on the left minus this entity evaluated on the right. This is the meaning of, right, these brackets. Big brackets enclosing an entity means this. Is it all right? Hello?
Yes, sir.
Yes, sir.
ul minus ur divided by f of ul minus f of ur divided by ul minus ur. This is called Rankine-Hugonet jump condition. So look here, the discontinuity has to satisfy this condition. So what did I say? A discontinuity has to be fitted, but this discontinuity is not arbitrary, right? It has to satisfy this condition. It has to satisfy this condition. This differential form is equivalent to this integral representation if u and its partial derivatives are continuous. Indeed, because it includes discontinuities as well. And this discontinuous curve which we have introduced, across which u and its partial derivatives are discontinuous, cannot be arbitrary. It satisfies this condition, which is known as Rankine-Hugonet jump condition. This is a very important condition. I tell you, you see, all these ideas, they were developed in mechanics. But this kind of representation in terms of a simple mathematical model is of a very recent origin. It is not very old. It is of very recent origin. You see, the father of this theory, you know who is this? Hello, who will tell me? Do you know someone? Hello? Have you heard the name of Peter Lex?
No, sir.
Hello? Peter D. Lex. P.D. Lex. Have you heard this name?
No, sir.
No, sir.
No, sir. This first time we are listening.
Pardon?
This is the first time we are listening this name.
No, this is the first time you are hearing this name? First time?
Yes, sir. Yes, sir.
Oh
Yes,
my
sir.
God. You see, he's the winner of this Abel Prize. Abel Prize in 2005 or 2007. I don't remember exactly the year, but he got Nobel Prize. It is I mean, equivalent to Nobel Prize, right? In mathematics.
In which field?
Sir, his
Mathematics.
name is related to fluid dynamics.
Exactly. You can see such equations. In fact, they appear in fluid mechanics, solid mechanics, plasma, everywhere almost. I mean, they're all pervading. But this man has done a lot of work on partial differential equations. Peter D. Lex on hyperbolic systems. He has worked on hyperbolic systems. You see, he's a man of analysis, partial differential equation and analysis, right? Not exactly he's a man of fluid mechanics, but of course, these equations, they do appear in fluid mechanics, they appear in solid mechanics, they appear in plasma, right? Everywhere. I mean, there are various branches of engineering here. I tell you that he's still alive, do you know? This person is still alive here at Courant Institute. Have you heard of Courant Institute?
Yes, sir.
Courant Institute of Mathematical Sciences. Courant Institute of Mathematical Sciences, such a wonderful person. You see, I met him. I was there during 2000, perhaps it was 9 or 10. During 2010, I met this person, and such a noble person, down to earth. And he told me, Professor Sharma, I am confident that this topic is extremely important and it is capable of producing some wonderful results. He told me like this, although I have not been able to do so, but I am sure one day perhaps something come up. Oh, I was surprised. What a great man. He has done wonderful, remarkable work in this area. So what I say, this is called Rankine-Huguenot jump condition, okay? Rankine-Huguenot jump condition, what it does, it connects the jump in the density function, jump in the flux function, and the slope, or you can say the speed of the characteristic curves. Or you can say dx dt, it is the slope of the characteristic as a matter of fact. It is the speed of discontinuity, In fact, this discontinuity need not be a characteristic curve. If it turns out to be a characteristic curve, then it is called a characteristic shock. I will come to that point a little later. Right? This is the discontinuous. This is the curve across which u and its partial derivatives are discontinuous. So this condition must be satisfied across it. Speed of discontinuity of this curve. All right. So now what is the problem? Now the problem reduces. To solving a differential equation, right? By just using these conditions, dx dt is equal to jump in f divided by jump in u. Correct? So let us consider an example. Consider one example. Consider this case that ud plus ux equal to 0 and u at x is equal to 0, it satisfies this condition. What is that condition? This is your 1 when x is less than 0, and this is 0 when x is greater than 0. Hello? I will take the other way. Sorry, this is all right. It's okay. This is it all right? Hello? This is your u naught x, okay? This is your u naught x, initial condition. Is it all right? Hello?
Yes, sir.
ut plus ux, I told you last time, Burger's inviscid equation.
Yeah.
This is your initial data. So if you look at the initial data, how does it look like? This is your ux plane. So this is your u naught x. This is x. At x less than 0, it is 1. Right? When x less than 0, when greater than 0, it is 0. So this is one problem. Yes. I could have taken this data to be, all right, I will do it a little later, but let me write this. This is another differential equation. X less than 0. This is x greater than 0. Okay? And this is your u naught x in this case. Is it all right? So let us consider the first one, okay? Let us consider the first one. These two different initial conditions. Consider the first one. I can quickly write the characteristic equations. Now you know how to write the characteristic equations, right? dx dt along the curves, dx dt is equal to u remains constant. It is very clear here. And what is u is equal to u remains constant? That is u naught of xi. Is xi here? Xi is this typical curve, characteristic curve, right? Originating from xt and intersects the line t equal to 0, right? We have talked about it so many times. So along these curves, u remains constant. U naught xi is the value of u at this point, okay? Is it all right? Hello?
Yes, sir.
So we get, what are the characteristics? Along these characteristics, now u is constant, because u is constant, so it will be your xi plus t times u naught xi. Along these characteristics, u is equal to u naught xi. This is the analytical form of the solution at, right? Various places I have written these equations.
Yes, sir.
All right. So now you can see here that what happens to the solution. The solution is now, what you have to do, this is your, look at the initial data. Now, if you look at the initial data, for here, this is your t-axis and this is your x-axis. At t equal to 0, what is the distribution of u? On the left of this, here u is equal to 1. On the right of this, u is equal to 0. Characteristics are straight lines. What they will do, they will carry this information into the region. Whatever the information is available here, the same information would be available at every point on this characteristic curve through this point xt. Is that right? Hello?
Yes, sir.
So tell me, what are the characteristics originating from the points of the initial line? Hello? I mean, x less than 0. The characteristics originating from characteristics originating from the points x less than 0. Means xi is an atypical point here. So these are the characteristics. Hello? They will take
equal to 1.
They will take this information u is equal to 1 into the region. So this is your leading characteristic. This is your leading characteristic, x is equal to t. And these are the characteristics, in fact. They carry this information from, and it is your u is equal to 1. All right. What are the characteristics originating from this part of the real line, x greater than 0? Hello?
U equal to 0.
Yes, x is equal to, I will write xi plus, these are the characteristics. The characteristics originating from x greater than 0, what are these? These are the vertical lines. Am I right?
Yeah, x equal
Carry this information.
X is equal to xi.
x equal to xi.
X is equal to xi. Very right. X is equal to xi. These are the vertical lines. These are the vertical lines. X is equal to xi. These are the vertical lines. So what do we notice here? On the left, the solution is 1. On the right, the solution, these are the all characteristic curves, right? This is your multi-valued region. This is your multi-valued region in the xt plane. This is your multi-valued region. Is that right? Hello?
Yes, sir.
Yes, sir.
So what is to be done? This theory tells us that multi-valued region is to be replaced by this discontinuity. The multi-valued region is to be displaced, is to be replaced by fit this discontinuity into the region, right? Satisfying all these conditions. That is, on the left, u is 1. On the right, u is 0. On the right, u is 0. So what is that discontinuity? Look here. dx dt. Now I'm trying to find out how does it look like? What is the shape of this discontinuity, the locus of the discontinuous curve? It is f of ul. What is f of u here? Yeah, right. F of u. Now look here. The correct one conservation form could be like this. I can write u square upon 2 x equal to 0. Hello? Hello?
Yes, sir.
Yes, sir. Yes, sir.
But the fact is this, you see, I can derive infinite number of conservation laws. From here I can also write u square upon 2 its t derivative. If I multiply it by u, right, it gives me u cube upon 3x derivative. This is equal to 0. In fact, I get a sequence of these conservation. Hello?
Yes, sir.
I get a sequence of these conservation laws, namely u to the power n divided by n, its t derivative, plus u to the power n plus 1 divided by n plus 1 into its t derivative. This is equal to 0. That is, from a given conservation law, I can derive infinite number of conservation laws. Yes or no? Hello?
Yes, yes, sir.
Yes, sir.
This is an example. But we will see that the weak solution of this is different from the weak solution of this. Although all these conservation laws, they have been derived from the single equation, but they are not equivalent with respect to a weak solution. So this is the problem. This is the problem. Although we have generalized the notion of solution, we say weak solution, which includes discontinuities as well, and we say that in order to get this solution, this multi-valued reason is to be replaced by a discontinuity satisfying this condition. But in this process, we have lost uniqueness on 2 counts. Number 1, from a given conservation law, infinite number of conservation laws can be derived, right? So this is one difficulty which a mathematician cannot solve. Because a conservation law, this is the job of a physicist or a biologist or an engineer, right? They do this modeling. Mathematics, man cannot do job. This is difficult. Okay. So anyway, the thing is this, that but if we just resort to the physics of the problem, yes, we can find one unique conservation law. And if the unique conservation law is fixed, then we can take care of this, this problem that there are infinite number of conservation laws. We would say, no, all right, this is not physically valid, this is not physically valid. Engineers and biologists and chemists, they will say, no, this is the correct one, this is the correct one. So even if the conservation law is correctly identified, there are initial value problems which don't have unique solution. This we will see. So is it all right, please? Up to here it is okay. Dx dt will be your, yes, exploit. Hello, invoke this result, jump in f, that is f of ul. So assuming that this is the conservation law, assuming that the evolution of u is governed by this conservation law. So what is f here now? Tell me quickly. F is
U square by 2.
u square by 2. So 1 by 2 f of ul. F of ul is ul square minus ur square divided by jump in u. Jump in u is ul minus ur. What do we get? This is nothing but half of ul
plus ur.
Is it all right? This is so. I will fit a discontinuity into this multivalued reason. I will replace this multivalued reason by a discontinuity. That is, here ul is 1, ur is 0. So x is equal to t by 2. It originates from 0 because you see the multivalued reason starts right at the 0 because all these characteristics, they start intersecting right at the origin. So a discontinuity has to be fitted right passing through origin, and this is your u is equal to, here on the left u is equal to 1, on the right u is equal to 0. So the solution you can write that u is equal to what is the solution? On the left it is 1, it is less than t by 2. On the right it is x greater than t by 2. This is the solution.
So it is not visible.
Should be visible. No, what is the problem?
Scroll up. The sheet, sir, sheet को ऊपर की.
लेकिन दिखाई तो दे रहा है. I can see it. I can see it.
Now it is visible. The last line, no, sir. The last lines.
Are you not able to see the last line?
No,
sir, it is
now it is
visible.
visible.
U is equal to, I have written U is equal to 1 when x is less than t by 2. Is it visible?
Now it is visible. Sir.
Yes, sir, it's
You can
visible.
scroll up the paper, sir. You can scroll
Okay.
it up. Paper. Yes. Now it's there.
All right. So the solution is U is equal to 1 when x is less than t by 2, U is equal to 0 when x is greater than t by 2. This is the solution to this problem, right? I have replaced this. I'll show you this paper. This multi-valued reason. This multi-valued reason is replaced by a discontinuity, right? Is replaced by a discontinuity such that UL on the left it is 1, on the right it is 0. So this is the solution. This is the solution. This is your solution. This is 0. X is equal to t by 2. Here on the left is U is equal to 1. On the right, U is equal to 0. That is the constant state on the right is joined to the constant state on the left through this discontinuity. So this is a solution which satisfies, you can see here, it's a constant state. It satisfies the differential equation identically. You can see here, ut plus ux, u is equal to 1 satisfies it identically. Hello? U is equal to 0, it satisfies it identically. Yes, only U is equal to x by 2, but x is equal to t by 2 on this discontinuity. On this discontinuity, this t by 2 satisfies the RH condition which has been derived from the conservation law, and therefore it's a weak solution. It's a weak solution. Your method of characteristics fails here, right? We cannot determine the solution using the method of characteristics. We have to extend the solution beyond this. So what happens? The thing is this, that here, because this is your, you see, the method of characteristics, what happens? Gamma is here, and we determine a solution in the neighborhood of this, provided gamma is not a characteristic. Here, characteristics, they start intersecting right at the origin. Here, the characteristics originating from different points, they start intersecting right at the origin, right? Hello? All those characteristics which emanate from here, they start intersecting right at the origin. Is that right? And therefore, it is not possible to find the solution in the neighborhood of gamma equal to 0. It is not possible. Your method of characteristics fail. Classical methods won't work. So then this is a weak solution. Why is it a weak solution? It's a weak solution because it ceases to be differentiable. It is not continuous across x equal to t by 2, right? It is not continuous across t by 2. It is discontinuous, so it's a weak solution. I said, just before a few seconds, I said that uniqueness is not resolved because if I take this as the conservation law, u square by 2t plus u cube by 3t x equal to 0, if I take this as the conservation law, okay, can you tell me that what is dx dt in this case? If this is the conservation law, then dx dt, because the flux function is changed, right? The flux function is changed. The flux function 2 by 3, what is the flux function? U cube by 3. What is the density function? U square upon 2. So you can write UL cube minus UR cube divided by UL minus UR. This is your RH condition, and RH condition gives you this UL minus UR, because they are different, this factor cancels out. You get UL square plus UR square plus UL. Is that right? You can see here that this expression is different from this expression. In the earlier case, you got only UL plus UR upon 2. This is the slope, this is the speed. This is the speed of the discontinuity, and its reciprocal will give you the slope. Its reciprocal will give you the slope in the tx plane. So this slope is different from this slope. So obviously, but in this case, what happens? In this case, UL is 1. Hello? UL is 1 and UR is 0. So what is the curve? Tell me quickly. X is equal to 2 by 3t plus 0 originates from 0. So this is all right. X is equal to 2 by 3. So the curve is different now, right? X is equal to, this is your discontinuity. Here u is equal to 1 and here u is equal to 0. A constant state is joined. So the solution in this case, uxt at any time, it would be 1 when x is less than 2 by 3t. Here 0 when x is greater than 2 by 3t. You see, these two solutions are different. Can you see here? So it is the same differential equation, but if they are, and it corresponds to infinite number of conservation laws. So it is very clear that weak solutions of these conservation laws, they are not equivalent. Weak solutions are not equivalent. Is that right? So you see, we have extended the notion of solution, but in this process, we have lost uniqueness on one count. That is, for a given differential equation, there exist infinite number of conservation laws. But this problem can be resolved, right? This problem can be resolved using, some experimental facts that, yes, what is the correct conservation law? This is possible. But even if it is done, there are problems where the uniqueness is lost. Even if you pick up a correct conservation law, okay, all right, this is not possible, this is physically not possible, this is the only physically possible case, then there are examples in the literature where the solution need not be unique. Quickly, I will give you one example. Yes, I have already written here, ux0 is equal to, this is the second one. You see, second one, look at second one. So quickly you can see that what is the solution, what are the characteristics emanating from the left. These are the characteristics emanating, this is your x-axis and this is your t-axis. The characteristics originating from this part, here u is equal to 0, for x less than 0, here u is equal to 1. So these are the characteristics emanating from this part of the real line. These are the characteristics emanating from this part of the real line. Look, there is a gap. In this triangular shaped region, there are no characteristics, right? So in fact, our data is unable to control the solution in this gap. And because of this, the solution need not be unique. Look here, one solution is, because we know that characteristics consist of straight lines. So one solution can be obtained just by drawing all these straight lines, which are the characteristic lines originating from this point 0, 0, carrying all the values of u between 0 and 1. Carrying all the values, this is u is equal to 0, this is u is equal to 1. All these lines, they carry all the values of u between 0 and 1. These are the characteristics originating from 0. So what is the solution to this? You can see here, when xi is equal to 0, what do you get? T times u naught xi. Xi takes all the values between 0 and 1, okay? Xi takes all the values between 0 and 1 on this interval. So u naught in fact is your x by t. This is one solution, obvious solution. You can see it satisfies the differential equation identically. ut plus ux. Let us see what is this expression. Ut will be your minus x upon t square. U is your x by t. Ux is 1 by t, identically 0. So this is right. It satisfies the differential equation identically. So this is one solution. uxt, I can write that 0 when it is less than 0, right? And it lies between x lies between 0 and x is equal to, right, t. Is that right? This is x is equal to 0, this is x is equal to t. So x lies between 0 and t. And here it is 1 when x is greater than t. This is your x is equal to t. So this is one solution. You can see it satisfies, it is a constant state, satisfies the differential equation identically. This satisfies the differential equation identically. This also satisfies identically. But the thing is this, there is no discontinuity. So look here, initial discontinuity in the data is resolved into the solution. It's a wonderful thing. It is only because of nonlinearity involved in the equation. So you see, nonlinearity plays a very important role. Initially, the data is discontinuous, but this discontinuity is resolved immediately thereafter. Can you say that it is a C1 solution? Hello? Is it a C1 solution? Quickly tell me. No, it's not C1 solution because across these lines, the derivatives are discontinuous. Please check it and ask me next time whether you are able to get this idea. I say it's a weak solution. It's a weak solution because the derivatives are discontinuous across the boundary. X is equal to 0 and x is equal to t. Right? So this is one solution. The other solution could be you fit a discontinuity as we have done earlier. So the other solution could be, yes, fit a discontinuity, this satisfying the RH condition that we have already seen on the left, 1, 0, here it is 0, 1, so it is going to be x is equal to t by 2, right? And these are the characteristics emanating from here. These are the characteristics. So u is equal to 0, and these are the characteristics emanating, hello, these are the characteristics emanating like this. Is that right? These are the characteristics. Oh, I'm sorry. X is equal to, yeah, this is okay. X by t. So I have.
Yes, that will be like.
That's just 1 minute. The solution should be, because this is one solution. The other one, you introduce a discontinuity. X is equal to x is equal to t by 2, right?
Yes.
X is equal to t by 2, and this is your x is equal to t. So this is the state u is equal to 1, and this is the state u is equal to 0. These are the vertical lines. These are the vertical lines. So solution extends up to the discontinuity, and here the solution extends like this. So you can see here u is equal to 1 extends up to the discontinuity here. So this is one solution. You can see it also satisfies the differential equation. 0, x less than t by 2, 1, x is greater than t by 2. So there are two solutions. In fact, I can have infinite number of solutions. So the problem is this: we have extended the notion of solution, namely weak solution, but in this formulation, we have lost uniqueness on 2 counts. Number 1, non-uniqueness of the conservation laws. Number 2, non-uniqueness of even if the conservation, this is resolved. Even if uniqueness is specified that yes, there is a unique conservation law, there are problems like this where there are infinite number of solutions. Now, so how to resolve this problem? This problem was resolved by Peter Delax, and tomorrow we will talk about it, that what did he say and why did he say. The proof of the result is extremely difficult. Perhaps this cannot be covered, but I will give you an idea that how does it work. Okay, some motivation about the result. So is it okay? There is any question, please? Time is up. Hello?
Yes, sir. Time is up.
Is there any query from anyone?
No, sir.
Okay, all right. So we meet tomorrow.
Yes, sir.